Howdy, folks. So today we're going to be talking about the norm of a vector that's living in an inner product space. So all an inner product space is it's a vector space that has an inner product defined on it. So over here on the side, I've got our 5 features of our definition for an inner product. The inner product of 2 vectors is always a real number. The inner product is commutative. We have this kind of distributive action happening here. Here's a property for scalar multiplication. And then the inner product of a vector with itself is always greater than 0 if the vector is not the 0 vector. And when we're talking about the norm, this 5th feature is going to be instrumental in our definition. Okay, so we're going to need the inner product of a vector with itself to be positive, so long as we are not 0. So we've got a bunch of definitions to define to get us going, and then we'll work through some properties and some examples afterwards. So let's start by defining what we mean by the norm. So the norm of a vector in a vector space V is defined to be okay, now it's going to look like I've got a double absolute value bar. So I've got 2 vertical lines, V. So that's going to be our notation for the norm. This is going to distinguish norm from just absolute value. Okay, so absolute value is kind of a scalar concept. The norm is a vector concept. So that's why we have different notation. And this is going to be the square root of the inner product of a vector with itself. So this is why we are using this fact that the inner product of a vector with itself is always 0 or bigger, because we're going to need to square root it, right? Okay, but that's not where this definition ends. Oh no, my friends. So next, once we can define like the length of a vector in a vector space, we can now define distance between vectors. So the distance between vectors U and V in our vector space, or in an inner product space, is defined to be, now the notation I'm going to use for distance is going to look like d of u v. Kind of looks like a function notation here where we have our distance of those 2 vectors between them. This is going to be the norm of u minus v. And this matches what we know and love about vectors in R2, right? So if I have 2 points and I want to find the distance between them, then I can subtract the 2 points and find the square root of the sum of the squares of the components. That's essentially, this is the generalization of that concept. And then lastly, we have 2 more definitions, but they're related. A vector V is a unit vector if the norm of that vector is 1. The set of all unit vectors in our inner product space V is called the unit ball, or sometimes the unit sphere in V. So what you want to be thinking about here is think about like what you know and love from R2, right? We live over here, we're familiar with this. And if I think about all of the points that are within a distance of 1 from the origin, we get the unit circle, right? If I'm in R3, we get a unit sphere. So this is why we're calling this the unit ball, because what we know about Rn has a ball-like shape. It's a sphere or a circle. So the collection of all unit vectors, so they have length 1, in a vector space is going to be called the unit ball or the unit sphere. So now that we've got some definitions underway, let's talk about a few properties of norm. Alrighty, so this is, scroll too far, this is theorem 14. These are properties of norm. And if you would like to pause the video here to copy these down or to think and reflect on them, you can. But I'm just going to talk about all of these 7 properties that we're looking at and try and relate them back to what we know about just regular old vectors in Rn. So the first one says that the norm of a vector is non-negative. So if you take the length of a vector, the smallest you can be is 0, otherwise you're going to be a positive number. And this makes sense because our definition of norm is the principal square root. So since we're taking a principal square root, we can't get a negative value. Then we also have that the norm of a vector is equal to 0 if and only if the vector itself is equal to 0. And that kind of harkens back over here to part 5 in our definition for inner product. If you take the inner product of a vector with itself, you get something that's bigger than 0. So if you take the square root of something that's bigger than 0, you're going to get something that isn't 0. So the only way you're going to get a norm of 0 is if you have the 0 vector. Then our third one here, be careful with this notation, it looks a little wonky. So I'm taking the norm of a scalar multiple of a vector v. That's the same as the absolute value of that scalar times the norm of v. So this is why I was saying the notation's a little funky. So here's our norm of v. Notice the double lines here. And then k is a scalar, so it gets the absolute value. So again, our norm is going to be a positive value. So that's why we have to take the absolute value of that k, right? So if I multiply a vector by -7, it's going to stretch it 7 times and change the direction. The norm doesn't care about the direction, it just cares about the stretch or the shrink. Okay, so that's why we're doing the absolute value of k. Property 4 is just a rewriting of our definition. So if I have, let me see, I'm going to make myself big so we can look at the board for a second here. So in our definition here, we have that the norm is equal to the square root of the inner product. So if I wanted to, I could square both sides and get this property that the inner product is equal to the norm squared, right? So that's all that the 4th property is saying. It's just a rewriting of the definition. I'm going to shrink myself again, see if I can do that. There we go. All right, so for our 5th property here, a couple things going on here. So first, I'm going to take the norm of the vector. So if I take my vector and basically I divide the vector by the norm, I'm taking the vector and I divide it by its length, that's going to result in a unit vector, right? Because I've taken, think about if you take a vector in R2, right, and you divide by its length, now its length is 1. So that's what we're doing here. And not only is this going to give me a unit vector, but it is a unique unit vector. That's a positive multiple of our vector v. Again, we got to make sure v is not the 0 vector because then we have division by 0, and that's just not nice, right? Number 6 is a super important and famous inequality. This is called the Cauchy-Schwarz inequality. And it says, if you square the inner product of 2 vectors, that is less than or equal to the square of the norms of those vectors. And you get equality holding only when one vector is a scalar multiple of another. So this is an inequality that in our class, we're not going to be using too much, but it is one of those like important and fundamental properties for linear algebra. Yeah. And in fact, if you go on to study more math, you will see a Cauchy-Schwarz inequality in lots of different spaces. Similarly, the triangle inequality is very famous, very often used inequality. And this says if you take the norm of the sum of two vectors, that is less than or equal to the sum of the norm of those two vectors. This one you can think of as like this shortest distance between 2 points is the straight line between them. Again, our vector spaces needn't be Rn, but that's how we tend to think of things. So if I look at what my triangle inequality is saying, is if I have, let's say that this is U and this is V, then this is U plus V. So this distance here, this norm, cannot be larger than this distance plus this distance, right? It's going to be less than or equal to that. And it's going to be equal if U and V are on the same line. Again, living in the land of R2, just to kind of relate it to something we're familiar with. But when we generalize this concept, we may not have that same picture in mind. All right, so now that we've got some properties of norm under our belts, let's do some examples. So we're going to do basically 3 examples. We've got one more definition, but it's a short definition and it flows with these examples. So as we did in the previous video, when we looked at examples using different inner products, I'm going to use different inner products and different inner product spaces for each example, just so you get a sense for what each of them is going to be like. Oh, excuse me. So I'm going to quit sharing. I'm not going to scare you either, but I'm going to stop sharing the screen and we'll write some examples on the board. Alrighty, so to just put it back in our heads here, I've written down a summary of what we know about some common inner product spaces. And this is going to be one of those situations where if I don't specify a specific inner product, these are the ones that we're going to be using. So if I'm living in Rn, my inner product is the dot product. So it's the summation of the products of the corresponding coordinates. In Mn, the inner product of our 2 matrices is going to be the trace of AB transpose. And if I'm living in P2, then the inner product of the 2 polynomials, super similar to the dot product, is going to be the sum of the products of the corresponding coefficients. And then I have just our definitions from today, from this video. Here we have our norm of V, and this is our distance between 2 vectors. So for example 24, they want us to find the norm for this vector, and we're living in R4. So we're going to use our usual dot product in combination with our definition here. So yeah, let's just work through that. So the norm of V is going to be the square root of the inner product of V with itself. And until I become super comfy with these definitions, always going to make sure I write them out first. Okay? So this is going to be the square root of, when I do an inner product, or like the dot product, I'm just going to basically be multiplying each entry times itself, right? So this V is both U and V from this definition now. So I've got -1 times -1, 3 times 3, -5 times -5, and 1 times 1. Oops, that should be a -1, sorry about that. So this is going to give me the square root of 1 plus 9 plus 25 plus 1. This gives me 10, this gives me 26. So that's going to give me 36. And since this is a principal square root, I just get 6. So there we go. So that's a norm of our vector in R4. So next, let's step it up a notch in both our space and in what it is we seek. So let's depart the nice safe land of R4 and we'll go to a land of matrices. Oh my. And forget easy norms. Let's do a distance. So that's going to be example 25. All right, folks. So this time, as I mentioned, we're living in the land of matrices. So not too terrible though, because they're 2 by 2 matrices. And what we're going to do is we're going to find the distance between these 2 matrices. We've got matrices floating around, that's our space. How do we find the distance between them? So if I look at our definition here, first we're going to need to subtract the two vectors, and then we're going to find the norm of those. So let's first subtract these two, and then we can find the norm. So we'll do A minus B. So this is going to give me 2 minus -1, which is 2 plus 1, or 3. 4 minus 0 is 4. 3 minus 7 is -4. And 6 minus 2 is a +4. So this is going to be my first step, finding A minus B. Next, I need to find the norm of this. So to find the norm, we need to find the square root of the inner product. So I'm going to find the inner product of this with itself first, and then we're going to square root it. So the inner product of A minus B with itself is going to be the trace of A minus B times its transpose. Again, I'm just writing out what it is I'm going to be doing so that I'm comfortable with these definitions until they become like a part of my heart and soul. All right, and then so A minus B is this matrix we took some time to find. And then we're going to multiply it by its transpose. So 3, 4 now becomes the first column, and -4, 4 becomes the second column. And now we multiply. So we get, let's see, 9 plus 16 is 25. -12 plus 16 is 4. -12 plus 16 is 4. And 16 and 16 is 32. Oh, and I dropped my trace. I don't want to do that. So this is my trace of all of that. So remember, the trace means just add the diagonal entries. So we get 25 plus 32. So we get 57. All right. So we just found the inner product of these differences. So we found this component. What we need is the square root piece. So lastly, the distance between A and B is going to be the square root of 57. Now, the only factors of 57 other than itself and 1 are 3 and 19. So we can't simplify it any further. So this is going to be our solution. If it was a radical that we could simplify further, right, maybe there was a perfect square factor, then we would, of course, simplify the radical and move from there. All right, so we have one more definition to do, and then we'll do an example of that definition. So give me a second to erase the board, and then we'll walk through it. All righty, so our last definition is definition 15. And this is to normalize a vector, what that means. So to normalize a vector V just means to find the unique unit vector that is a positive multiple of it. So when we were talking about our properties of norm, we said that we could find that by doing 1 over the norm of V times the vector V itself. So that's going to be our method that we do. Our first step will be find the norm of the vector and then multiply by that vector. So since we've done an example using the dot product and we've done an example using matrices, it seemed about appropriate to do an example using P2. So here's our vector Q. It's not written in standard form. So in order to apply this definition of the inner product, we want to put it in standard form first. So this is a difference of perfect squares, the factored form. Right, so Q is going to equal 1x squared plus no x minus 16. You don't have to write it this way. If you just wrote x squared minus 16, that's fine. I just chose to write it in this manner so that when we go to find the norm of Q, we'll know where the numbers are coming from. So speaking of, let's find the norm of Q. So the norm of Q is the square root of the inner product of Q with itself. So this is the square root of the inner product of Q with itself. So that means, just like we did with our dot product, basically you square each component, we're going to be squaring each coefficient. So I'm going to do 1 times 1 plus 0 times 0 plus, oh gosh, negative 16 times negative 16. I think that's 256. So this ends up giving us the square root of 257. You know, a nice, beautiful radical for us to work with. It is not a perfect radical, so we're just going to leave it be. And then now we'll normalize Q. So to do that, we're going to take this definition of Q and divide it by this value. So we're going to do 1 over the norm of Q times Q. So 1 over root 257 times x squared minus 16. Now we don't want to have radicals in the denominator, so we have to rationalize the denominator. That's going to give us the square root of 257 over 257 times x squared minus 16. And then just to give our answer in standard form, this is going to be x squared square root of 257 over 257 minus 16 square root of 257 over 257. Da-da-da-da-da-da. Hooray! All right. So yeah, so that's our beautiful, gorgeous answer. It's fine. It may be irrational, but that's all right. Well, we'll let it be. Now, I will mention that for our final answers here, I am going to be expecting answers in simplest form. So even though this doesn't look simple, it is going to be considered our simplest form with our rational denominators. But if I am doing this in the context of a larger problem, which we'll be seeing in the weeks to come, then we may wait to do this rationalization till the very end. So what I mean by that is if finding a norm is a middle step of a problem, which it will be in the future, then I might leave it like this until I've gone on to the next steps of the problem. Because sometimes these radicals get, vanished because we end up squaring stuff. So then this process would have been just wasted effort. We don't want to waste any effort. So that's where we're going to stop here today. And in fact, that's where I'm going to stop for this week. Just these 2 short videos about the inner product and the norm. So yeah, so we'll be talking about these next week. In the meantime, I hope you have a wonderful day. And yeah, we'll see you next week when we start to talk about orthogonal vectors or perpendicular vectors in an inner product space. So that's what we'll be seeing in the future. In the meantime, have a wonderful day and yeah, see you around. Bye.